In this lecture, we will talk about Fourier transform pair, complex number expressed in terms of the polar coordinates. In the Cartesian or rectangular coordinate, any complex number c tilde k, for example, can be expressed as the real part, which is r sub k, plus the imaginary part, capital I sub k, times small I. And remember again, the definition of small I is that I squared is equal to minus 1. However, if we express the complex number instead of in the Cartesian or rectangular coordinate, if we express that complex number in the so-called polar coordinate, then that complex number c tilde k can be expressed as equal to an amplitude equal to capital A times e raised to the power I theta. And the angle theta is the angle, or some people call it phase angle. Now obviously, according to the so-called Euler identity, we can say e raised to the power I theta is the same thing as cos of theta plus I psi theta. This is based on the so-called Euler identity. We refer to this relationship very, very often, Euler identity. Okay, so after expressing the EI theta using the Euler identity, then we can multiply A with the cosine term. Then we got this term, which represents the real part of the complex number c tilde k, and multiply A with I sine theta. Then we got the second term, which is A sine theta, represent the imaginary part of the complex number c tilde k. Now, in order for you to understand how to express the polar coordinate of the complex number, the next slides probably will help you a little bit better. As you can see on this picture, the horizontal axis that you have here represent the real component of the complex number, let's say r sub k. And the vertical axis represent the imaginary component of the complex number k. So if you have any complex number, it can be represented by, let's say, any complex number c or c tilde. That can be represented by the amplitude A, which is like the radius of this circle, the amplitude A, and also expressed by the phase angle theta. That angle right there is theta. So in polar coordinate, the complex number c can be expressed in terms of the amplitude A, which is the radius in this case, and the phase angle theta. On the other hand, for the same complex number, if you express that in terms of the Cartesian coordinate, then that complex number c can be expressed by the real component, which is r sub k, and the imaginary component, which is I sub k. Okay? So a complex number can be expressed either in terms of the polar coordinate or in terms of the rectangular Cartesian coordinate. Obviously, there's a relationship between the two systems, because for the real component r sub k, which is this distance right here, r sub k is equal to amplitude A times cosine of the phase angle theta. And similarly, the imaginary component in the Cartesian coordinate I sub k is given by A sine theta. So what I'm trying to tell you is that a complex number can be represented in the Cartesian coordinate by the real component r and the imaginary component capital I. Or it can be expressed in terms of the polar coordinate, such as amplitude A and the angle theta. Amplitude A and the angle theta. And the two systems, rectangular coordinate and polar coordinate, they are related by those two equations. Okay. According to the definition like that, then we can say r squared plus ik squared is equal to what? Well, from the previous picture, you can see the real part rk squared plus the imaginary part ik squared should be equal to a squared. As a matter of fact, if you look at the two formula here, rk equal to a cos theta, ik equal to a sine theta. So if you take the real part rk, you square it, and then you take the imaginary part ik, you square it, and then you add together, what you have will be rk squared plus ik squared is equal to, this is rk squared, and this one is capital Ik squared. When we add up together, we can factorize the term a squared. You can factor it out, which is in here. And what you have left is cos squared theta plus sine squared theta. And we all know cos squared theta plus sine squared theta is equal to 1. So basically, just say rk squared plus ik squared is equal to a squared. Or we can say the amplitude A is equal to the square root of the real part rk squared plus the imaginary part ik squared. So if we know the real part rk and the imaginary part ik of a complex number, then we can find out the amplitude A very easily. Now, the next thing is, how do we find out the phase angle theta? Well, again, it is very easy, because according to the previous slide, the angle theta, we can compute it based on rk divided by A, or can be based on ik divided by A. So from those two formulas, either of the two formulas, we can find out the angle theta. And that is exactly what I show you there. You can calculate the phase angle theta by using this formula, which is cos theta equal to rk over A. From that, we can find out the phase angle theta. Or we can find out the angle theta by using the formula sine of theta is equal to the imaginary part of k divided by A. And from that, we can find out the phase angle theta as well. So in principle, we can find out the angle theta either by the first formula here or by the second formula here. But in practice, you have to be very careful, as you will see in the example that I will explain to you in the next few slides. So to summarize it, if you have a complex number, let's say complex number C, you can express that in the rectangular Cartesian coordinate by specifying the real part rk and the imaginary part ik. Or alternatively, you can also express the complex number by figure out the amplitude A and